All right, good morning, everybody. Hope you guys are doing well today. So, we are going to continue talking about systems of equations. Today, though, I am going to transition into Chapter 7, Section 1, which is where they show us how to use systems of equations in a much cleaner fashion. Unfortunately, with this year and with um, the having cohort A and B, I was not able to go into the extent that I normally would go into when discussing these systems of equations. I would show you how to hand solve those. This year, we are not going to do that, so I am moving ahead into Chapter 7, Section 1, which is to show you how we can use graphing calculators, computers, things like that to organize this data and then use the capabilities of that equipment to solve it. And it actually is much, much, much easier to use graphing calculators and or computers to solve these systems and to not hand solve it. So in that way, you guys are kind of lucking out a little bit because I'm just going to show you how to solve these using a graphing calculator. So in order to solve these systems using a graphing calculator or any other sort of technology, could be computer, could be Excel, all these different things, is you need to be able to organize that data into a little cleaner and neater way. And the way that we're going to do that is we are going to take the data from those systems and we're going to put it into what are called matrices. Now, you may or may not have discussed what a matrice was in Algebra 2, but they're pretty straightforward and they're pretty easy. All they are is a simple way to organize data in such a way that it can be inputted into, for us, our graphing calculator. So it says, in this section, you will study a streamed line technique for solving systems of linear equations. This technique involves the use of a rectangular array of real numbers called a matrix. The plural of matrix is matrices. And what it shows you here is the definition of a matrix. And I know it looks really scary. It's like, man, what are they talking about here? And so let me show you a little bit of what they're saying. So a matrice first, it is defined with these giant brackets. You can see there's a bracket here and there's a bracket here like this. And those brackets encompass all of our data. And then what we have is we have rows of data, but you could also look at this and say we have columns of data like this. So this is a row across, this is a row here, okay? This is a column, all right? And the way that I remember that is I think of columns, right? Support columns hold your front porch up on the front of your house, for instance. So columns are this way, and then rows are the other way. Now, matrices, their size is actually called an order. So if you ask me, what is the order of the matrix? You're going to hear me say that. That just means what is the size of the matrix. And you always list it by how many rows and then by how many columns. And so why I'm telling you this is matrices can be as big or as small as we need them to be in order to list all of our data. And so if you look at these little numbers right there, that I know that looks like A sub 11. It's really not. It means A and then row 1, column 1. If we were to go down to here, for instance, this A sub 23, that's actually how that's pronounced, not A sub 23. It's A sub 23. That is row 2. So this is the first row, this is the second row. So that's this one right here is row 2, column 3. This is column 1, this is column 2, that's column 3. So you can see right here, it's A sub 2, 3. And the best way, the analogy that I always use every year to explain this to people is that old board game called Battleship. Now in Battleship, they used letters and numbers, right? So B4. A5. In this case, we're not using letters. It's just the first number represents the row, and then the second number represents the column. And another thing to keep in mind is if the row and the columns are the same, 2, 2, 3, 3, 4, 4, it means you will have what you have is called a square matrix because you guessed it, the matrice that you get or the matrices that you get are perfect squares. They have the same number of rows as they do columns. So the first answer here, and unfortunately, when I take my PowerPoint slides and put them as PDFs, it actually has the answers written there. But the first example that I want to look at is um, just to determine the order of each matrix. So remember, the word order, as I just said, is the how many rows and then columns. Okay, so it's always row and then column. So if you look at this one right here, this one only has one row this way and it only has one column this way. So therefore it is called a 1 by 1. Now, looking at this matrix, right? This matrix right here, we need to count how many rows. So how many times can we write a line across? And you can see there's only one of those. So the row is 1, but then when we look at the columns, there's 1, 2, 3, 4 columns. So this matrix is considered a 1 by 4. Now, looking at this one's kind of hard to mess up, right? Because the rows and the columns are the same. There are 2 rows and there are 2 columns. So we call this a 2 by 2, or in the last slide, as I said, that would be considered a square matrix. Now, D, again, we go count rows and then columns. So rows, 1, 2, there are 3 rows, and there are 1, 2 columns. So we call that a 3 by 2. So that's exactly how you find the order of a matrix. Now, later on, when we do more things with matrices other than just list their order, knowing their order is going to be very important for us to know whether we can perform certain operations, which we'll discuss later on in the section. Now, the next part, and this is where what I talked about taking data and be able to enter it into your graphing calculator to be able to solve it. It says a matrix derived from a system of linear equations, each written in standard form with a constant term on the right, is the augmented matrix of the system. It says, moreover, the matrix derived from the coefficients of the system, but not including the constant terms, is the coefficient matrix of the system. So I'm going to show you an example of what that is, because I know that's a lot of words and it seems like it could be confusing, but it's actually a pretty easy concept once you kind of understand what's happening. So right here, if you look at this system that we have, I'm going to highlight, here's our first row, right? That first row, it has 3 variables now. And as I said, we were going to be expanding and working into using more than 2 variables. But so we have an x, we have a y, and a z. So that's 1x minus 4y plus 3z equals 11. And so what I want you to notice about this augmented matrix that we have right here, if you look at the first row, they completely eliminated the variables. The x is gone, the y is gone, the z is gone, and the equal sign. And what you then realize is this is a much cleaner way to write that information because it's only the constant coefficients before the variables. And so I want you to look at this for a second and see that this is the x, this is the x, this is the x. And if you notice, all of the x's are lined up in a column. And so if you would go down that and you would look at the coefficients in the front, this one would be 1, this one would be -1, and this one would be 2. And if you look right here, you can see we have 1, -1, 2. So in a nutshell, all a matrix is the numbers from the equations lined up. They've got to be organized, right? So the columns of the x's line up, the columns of the y's line up, the columns of the z's line up, and then you can see there's no on the, whoops, I meant to circle this. Over here, there isn't any of the equal sign, right? So this is a coefficient matrix because it just has the numbers of the coefficients of the x, y, and z. Whereas this one right above it, the one that's not highlighted or that is highlighted, the augmented matrix, they include these numbers over here. And that's where these dots are. These dots right here just represent the equal sign. All right, so that's called an augmented matrix versus a coefficient matrix. Now, we will be mostly using augmented matrices and to do what we're going to do. Not always, but for at least the next couple of lessons, that's what we'll be using. So an augmented matrix is simply the constant coefficients. One thing that I want to note, if you look in this last equation right here, we have 2x minus 4z equals 6. Notice there is no y term. They left a space there, so all the z's are still lined up. When you write these, you need to make sure that you're keeping things organized by column. Notice there is no y term, so in the augmented matrix, you need to fill in a 0. If you'd had 0 times y, that's 0, right? And in the matrices that were not matrices, I'm sorry, in the systems that we've been working with so far, you didn't have to worry about writing anything there. But when you draw a matrix, you must put a 0 in there. If you don't, you will get all kinds of errors when you try to do what we're going to do next. And this just says exactly what I said. You have to use 0 for missing coefficients. So the first two examples here, for example 2, are just to write the following systems as an augmented matrix. So this is really, really simple. You're going to draw your regular straight bracket, right? So these are not squiggly brackets. Squiggly brackets go on systems of equations. Matrices use these big straight brackets, and you're simply going to write the coefficients of each one. So we have 1 going across this row first. We have 1, negative 2, 3, and then I'm going to put the augmented part. So we put our dotted line, and then we put a 9 after that. Then we have negative 1, 3, 0, negative 4, and lastly 2, negative 5, 5, and 17. Don't forget to close out your bracket on the other side so we know that it is a full matrix. And that's it. That's a coefficient. That's an augmented coefficient matrix. Very, very simple. We're going to do the same thing for B here. Just keep your columns organized. I can't stress that enough. Very important for your understanding as we work with these, that you're keeping things organized and neat. So we're going to do our dash line or dotted line, and then our augmented part is over there. And so then we have 4, negative 2, 2, negative 2, and then negative 6, 5, 4, and 10. So very simple. Just again, don't forget, as I said before, if there's nothing right here, you do need to put a 0 in. You have to list that 0. All right, now these two problems are the exact opposite of what I just did. So if you look in this problem, I gave you the system of equations. You needed to write the variables. I'm sorry, you had to write the matrices to the system. Now I'm going to give you the matrices and I want you to write the system. And as a general rule, if there are two columns like this, there's two columns, you're going to use X and Y. If there are three columns like this, you're going to use X, Y, and Z. That's going to be the most common letters that we use. So as I write across here, this system first would have a squiggly bracket, and it would be 2x plus 6y equals negative 4. And then the second one is negative 1x plus 8y equals 7. Just like that. Pretty easy. Next one, once again, you want to have a squiggly bracket, and if you want to know, some people might be thinking, well, do I have to draw that bracket? The answer is yes. That squiggly bracket represents those two equations being together and being graphed together or solved together. It's telling us this is a system. So you must use the squiggly bracket when you do this, and you must use the squared off brackets whenever you write a matrix. So this one's going to be 2x plus 7y minus 2z equals 0. Then we have 4x, and we're not going to write anything for y, but we are going to write minus 2z right here equals 6. Notice how I left a space, so I'm keeping all of my variables lined up in columns. And then this one doesn't have an x, but it does have negative 5y plus 2z equals negative 11, like that. And there is your system. Remember, when you also write a system, you do not need a squiggly bracket on the right-hand side of the system, only on the left. Matrices require brackets on both sides. So, all right. So that's it, guys. That should have been pretty straightforward for you. I would like you to try some problems in your book. And as always, if you have any questions, feel free to email me. Have a great day.